Hi everyone. Today we are going to study what is meant by heat capacity. Before that, let's revise what we have seen before. First law of thermodynamics. Mathematical statement was delta U is equals to Q plus W. Next, heat. H is equals to U plus PV. Now, change in internal energy at constant volume was equal to heat delta U is equals to QV. Because delta V equals to 0, so work done will be 0 and delta U equal to QV. And again, this relation was again modified as delta H is equals to delta U plus P delta V, right? And it was equal to the QP, right? We have seen this earlier. Now today let's start with heat capacity. What is meant by heat capacity? Before that, let's see. I have already told you that we cannot measure H and U as it is. We can only measure change in internal energy and change in enthalpy. But how can we measure this? Yeah, this is a very important question. This is measured with the help of heat, right? But how can we measure heat? The technique in which the heat is measured, that is change in energy in the form of heat is measured, the method is called as calorimetry and the instrument is calorimeter. What we do? We just do the process in the calorimeter and that device allows to happen the process. Process will happen in the container and the instrument is in such a way that there is no heat transfer outside the surrounding. Heat will not go outside, that is, it will not leave the system. And therefore that the heat will not leave calorimeter, so we can calculate the heat with the help of change in temperature during the reaction. We know that internal energy and temperature has direct relation. If internal energy increase, then temperature also increase, and if temperature increase, then absolutely internal energy will increase. So if we measure temperature change during the reaction, that is delta T, then with the help of calibrations we can have the value of Q. If the experiment is at constant pressure, then we will get QP, and if it is constant volume, then we will get QV. If experiment is at constant pressure, then that QP will be equal to change in enthalpy. In this way we will get the value of enthalpy, and with the change in enthalpy and at constant volume we will get the value of change in internal energy. So the process is calorimetry and the instrument used is calorimeter. Now let's move towards heat capacity. What is meant by heat capacity? Heat capacity is nothing but the ratio of heat required to raise temperature of the system to the change in temperature or rise in temperature. Let's have an example. We have beaker and water inside it. Now we are giving heat. We are heating that beaker. Now what will happen? Slowly, with time, the temperature of the water will increase. Now why the temperature will increase? Because water is getting heat from outside. So what it will do, this is our system now. System will store heat inside it, and due to that heat, temperature will increase. And therefore, heat capacity is what? Heat absorbed by the system divided by change in temperature, or the amount of heat required to raise the temperature of the system divided by change in the temperature or raise in temperature. This is denoted by C. Now, what will be the unit of heat capacity? It's just easy, as heat is the form of energy, and what is the unit of energy? It is joule. Now, what is the unit of temperature? Kelvin. So, joule per Kelvin is the unit of heat capacity. That's it. Now, heat capacity is, there are another two terms. First is molar heat capacity. It is denoted by CM. And another is specific heat capacity. It is denoted by CS. The term itself says what is molar heat capacity. It is just heat capacity of 1 mole of substance is nothing but molar heat capacity, and similarly heat capacity of 1 gram of substance is specific heat capacity. Now, if we have given the heat capacity of 10 gram of substance, 10 gram CV, we know, sorry, C, we know. Now, how will we calculate CS, specific heat capacity? It is the heat capacity of 1 gram of substance. Therefore, for 10 gram it is C, then for 1 gram it will be C by 10. That means, how we can calculate the specific heat capacity? It is just heat capacity divided by mass in gram. So, unit will be joule per Kelvin for this and per gram for mass. Therefore, unit of specific heat capacity will be joule per Kelvin per gram, and similarly for molar heat capacity, how can we calculate? It is just heat capacity divided by number of moles, where N is equals to number of moles of substance, and the unit will be joule per Kelvin per mole. And this is M is equals to mass of substance in gram. This is all about heat capacity. This is molar heat capacity, this is specific heat capacity. Now, let's study the relation between internal energy and temperature, or variation of internal energy with temperature. Now, we know that if we have a substance and we increase its temperature, what will happen? The constituent particles of that substance will rotate vigorously, will vibrate, and as well as they will have increased kinetic energy. It will increase their kinetic energy. So, what will happen to internal energy as whole? It will increase with temperature. So, as temperature increases, internal energy also increase. Now, we can say the graphical representation for that. If we plot internal energy with temperature, we will get the graph like this. Now, this is curve we obtain. if we have tangent to that curve, let's say here point A and here point B. These are two tangents, that is at different temperatures we have tangent to this curve. What will we get? See, the slope of this tangent will be equal to the heat capacity. How? Let's see. What will be its slope mathematically? Slope is y2 minus y1 upon x2 minus x1. So delta u, that is dabba u by dabba t. But see, this is at constant volume, okay? At constant volume. Therefore, dabba u by dabba t at constant volume will be the slope. Now, we are saying that this is a value of heat capacity. Then, how it is heat capacity? Let's see. See, delta U at constant volume. What is the value of delta U at constant volume? It is QV. So we can write QV by delta T at constant volume. Now, what is heat by delta T? We already seen C is equals to what? C is equals to Q by delta T. This is the heat capacity, joule per Kelvin. So this value and this value is the same, so it is the heat capacity at constant volume, and it is denoted by CV. Heat capacity at constant volume is CV, and this is equal to CV. Therefore, this and this is equal, because W at constant volume is nothing but QV, as we see here. So it is heat capacity at constant volume. This graph, the slope of this graph will give us value of heat capacity at constant volume. That's it. And again, for molar heat capacity at constant volume, CV by M. Molar heat capacity at constant volume. Molar heat capacity at constant volume will equal to CVM. It is denoted by CVM. Molar heat capacity at constant volume, it is equal to CV by M. And similarly, CVS, that is specific heat capacity at constant volume, will be CV by, it is N, number of moles, and it is M, mass of the substance. And unit will be joule per Kelvin per mole and joule per Kelvin per gram. That's it. Now let's see here, since delta U is equals to QV. Now this is all about temperature dependence of internal energy. Now let's see temperature dependence of enthalpy. C is equals to Q by delta T, heat capacity joule per Kelvin. Now, temperature dependence of enthalpy. How enthalpy varies with temperature? What is enthalpy? Enthalpy is total energy of the system. Now, as temperature increases, energy of system also increase. So, enthalpy also increases with increase in temperature. Now, it can also be shown in the form of graph like this. If this is enthalpy and we plot it against temperature, we'll again get one graph. From these points A and B, what we get here, let's come here again. From this graph, what we see, heat capacity, this slope, the slope of B, and this is slope of A, when we calculate, then we see that B line is like this and A line is like this. Then which one has more slope? Absolutely, this line will have greater slope. That means greater value of CV than A. Therefore, heat capacity at increased temperature, high temperature, heat capacity value is higher than that of at low temperature. This was a conclusion from this. But if we take heat capacity at smaller interval, let's see this interval, then here the heat capacity will be same, the value of heat capacity will be nearly same. So we take majority times we take the heat capacity value constant. Now again, when we draw the tangent to this curve, then we will get the slope again. This slope will be delta H upon delta T. Now we calculate enthalpy at constant pressure always. So at constant pressure, here pressure is equals to constant. Now delta H upon delta T at constant pressure, what will be it? This is actually slope now, but we know that delta H is equals to delta U plus P delta Phi is equals to QP. We have derived it in last lecture. So if the value of delta H will be QP, then what we QP by delta T, that is QP by delta T, it is nothing but C. Therefore, this slope will be heat capacity. It is equals to heat capacity, but it is now at constant pressure. This will be Cp. Heat capacity at constant pressure will be delta H upon delta T at constant pressure. Now what? Molar heat capacity at constant pressure will be equal to Cp by N, and specific heat capacity at constant pressure will equal to Cp by M, mass in gram, joule per Kelvin per mole and joule per Kelvin per gram. That's it. Now we have obtained these two values for heat capacity at constant volume and at constant pressure. Now let's compare these two. What will be the relation between these two? Cp and Cv. What will be the relation? Here W is equals to Qv. We know that W is equals to Qv, and here delta H will be equal to Qp, but Qp is equal to delta U plus P delta Phi, while Qv will equal to only delta U. Got it? This is the main difference. Here we can write delta U by delta U by delta T. Here we can write delta U plus P delta Phi by delta T. It will equal to delta U plus P delta Phi upon delta T. This is a major difference. So value of Cp will be greater than Cv. We can see here. Here only delta U, here delta U plus P delta Phi. Therefore, value of Cp is greater than Cv, and we can calculate Cp minus Cv. What it will be? It will be just differences of just P delta Phi. So if we calculate P delta Phi, we will get Cp minus Cv. Let's calculate Cp minus Cv. We know Cp minus Cv is equals to P delta Phi. How we will calculate this? Now we know that PV is equal to nRT for ideal gas. Okay, and if we have a substance and we are increasing the temperature of that substance by 1 degree Celsius, temperature increased by 1 degree Celsius, and what will be volume? Then what about volume? Volume will increase by delta V, right? If we increase the temperature by 1 degree Celsius, its volume will increase by delta V, because expansion will occur. With rise in temperature, heat content will increase, and that heat content will perform the work, and so expansion work will happen and the volume will increase by delta V. Now let's substitute here. P in bracket V plus delta V is equals to nR. This will be increased by 1 degree Celsius, so temperature will be T plus 1. Therefore, PV plus P delta V will equal to nRT plus nR. Therefore, PV is equal to nRT. It will be cancelled. Therefore, P delta V will equal to nR. Therefore, Cp minus Cv will equal to nR. This is important. Now, if we divide Cp, the whole equation by n, then what we will get? Cp by n minus Cv by n is equals to R, right? And what is Cp by n? Heat capacity at constant pressure divided by number of moles, it will be Cpm, while heat capacity at constant volume divided by number of moles, it will be Cvm. So, Cpm minus Cvm will equal to R. Okay, these are important relations. We got Cpm minus Cvm equals to R. Now we have seen W by T at constant volume equals to Cv. Now we can write W equals to Cv dt. Du is equals to Cv dt. Now we can integrate it. It is state function. So integration of du will be u, delta u will equal to integration of Cv dt from T1 to T2. Therefore, delta u will be equal to Cv delta T. T2 minus T1 will be delta T. We got delta u is equals to Cv delta T. And from this, we can calculate delta u by Qv, and from that, and we know we will count delta T and we will know the value of Cv. We can calculate in this way, we can calculate value of specific heat capacity at constant volume. Now similarly, we know Wh upon T at constant pressure is equals to Cp. Now Wh is equals to Cp, Dh is equals to Cp dt. Small, infinitely small values. Now if we integrate this, we will get delta H. It will be equal to Cp delta T. And here we can calculate Cp by delta H by delta T in this way. So we can have both values Cp and Cv. We can calculate them experimentally. Now this was all about heat capacity. We have seen now heat capacity. Now let's see one topic, degrees of freedom. It is important in many fields. It is used. Degree of freedom. Degrees of freedom, short form. So it is equal to 3n. In many cases, this relation is used. Degrees of freedom equals to 3n. Now, what is this 3n? These are total degrees of freedoms, and they are divided into 3 categories. First is translational degree of freedom. second one is rotational, and third one is vibrational. Now, how many translational degrees of freedom one molecule can have? These are maximum 3 translational degrees of freedom will be possessed by any molecule, because there are only 3 axes. So it will translate. Translational motion means this type of motion, walking. That type of motion will be performed along either x, either y, or either z. So there are 3 translational degrees of freedom. For rotational degrees of freedom, if the molecule is linear, that means like O2, CO2, N2, these type of molecules will have only 2 rotational degrees of freedom, while the molecules which are non-linear, like H2O, these type of molecules will have 3 degrees of freedom, rotational degrees of freedoms. Now remaining is vibrational. How can we calculate vibrational degrees of freedom? As we know translational, we know rotational, and total degrees of freedoms are 3n. Out of that, rotational and translational are these are. So we can calculate vibrational degrees of freedom. That will be total degrees of freedom minus sum of these 2. That is, if molecule is linear, then 5, 3n minus 5 for linear, and 3n minus 6 for non-linear. This is very important concept. Okay, why we are studying this actually? Here we have studied specific heat capacity at constant volume, and these degrees of freedom have contribution in heat capacity at constant volume. How? Molar heat capacity at constant volume, CVM. It can be calculated by number of translational degrees of freedom. Sorry, we will take it down. CVM will equal to number of translational degrees of freedom into R by 2. The translational degrees of freedom have contribution in heat capacity at constant volume by R by 2, plus number of rotational degrees of freedom into R by 2, plus number of vibrational degrees of freedom into R. This will be only at high temperature. At low temperature, it will be equal to 0. Why? Because vibrational motion will be very less at a very low temperature, and hence it will not contribute. But if temperature is high, then the formula is CVM is equal to number of translational into R by 2, number of rotational into R by 2, plus number of vibrational into R. Now let's see an example. For understanding, if we take molecule O2, O2 is our example. Now total degrees of freedom 3n, it will equal to 3n will be equal to 3 into n is number of atoms. Here are 2 atoms, O double bond O, these are 2 atoms, so 3 into 2 will be 6. Now these 6 are again categorized into 3. First is translational. How many translational? 3. Then rotational. How many rotational? It is linear molecule, so it will have 2 rotational degrees of freedom, 2. how many vibrational? 3n minus translational plus rotational, 3n minus 5. So 6 minus 5 will be 1. This is the scenario for O2 molecule. Now at high temperature, if we take it at high temperature, its specific heat capacity, molar heat capacity at constant volume will be translational 3 into R by 2 plus 2 into R by 2 plus R. It will be equal to 3R by 2 plus 2R. It will be equal to 7R by 2. CVM, value of CVM will be 7R by 2. Hence we have studied this whole thing. Now if we got CVM, then we can also calculate CPM. How? We have already seen the relation. Cp minus Cv is equal to Nr and Cpm minus Cvm is equal to R. So if we know Cvm, then we can calculate Cpm because R is gas constant, 8.314 joule per Kelvin per mole. So we will get the value of Cpm also. Now we have value of CVM, we have value of CPM, then CPM upon CVM is the special thing. It is called gamma. This is the gamma. This is also very important when we will start adiabatic changes. At that time, this is very important thing. CPM by CVM is equals to gamma. And yeah, the value of gamma will always be greater than 1. Why? Sorry, will always be greater than 0. Why this is so? Because CPM is higher quantity than CVM, so it will always give gamma greater than 0. Ratio will be always greater than 0. Or 1, we can say 1. Because CPM is greater than CVM always. Now our next point is isothermal expansion. First let's see isothermal reversible expansion. This is just revision part. We have studied it in our lower classes. Isothermal reversible expansion. We have already seen what is reversible and what is irreversible. So I will not repeat it. Isothermal reversible expansion of ideal gas. Okay. That means delta T is equals to 0. If we have seen just now that temperature, internal energy depends on temperature. So if delta T is 0, then change in internal energy will also 0 and change in enthalpy, total energy, it will also 0. Now let's have a container. It is filled with gas and here is piston, gas filled. Now it has pressure P1 and volume V1, temperature is constant. Now the expansion will occur. If there is expansion, then process is reversible. It will be P2 and this will be V2. What is work? We have seen work earlier. W is equal to minus P external delta V. Why? Because P external, so dV, we can write dV. Minus P external dV. Why? P external pressure is the force. We know work is opposing force into displacement. Opposing force is external pressure and P external, so force is P external and change is dV. So and here minus sign, it is opposing. P external is opposite. W is minus P external dV. Now how we will calculate work done for this process? This is dW. dW is minus P external dV, small change. So this is small work done. Now what will be W? W will be integration of V1 to V2 minus P external dV. It will be equal to, now what will be the value of pressure? We know PV is equals to nRT. Therefore pressure will be equals to nRT upon V. It will be minus in outside V1 to V2 nRT by V dV. It is equals to minus nRT constant outside integration of 1 upon V. What will be it? ln V from V1 to V2. It will be equal to minus nRT in bracket ln V2 minus ln V1. We can write it minus nRT ln V2 upon V1 W. This will be our work done. This is the work done in isothermal reversible expansion. Now what will be the heat? We know that delta U is equals to Q plus W. Now delta U will be 0. Therefore delta T is equals to 0. Therefore delta U is equals to 0. Q is equals to minus W then. So heat will be equal to Q is equals to minus W. It is equals to nRT. This minus sign will be neutralized. nRT ln V2 by V1. It can be also written as 2.303 nRT log V2 by V1, and also can be written as 2.303 nRT log P1 by P2. Why? Because PV is equals to constant, as temperature is constant, NR are constant. So P1 V1 is equals to P2 V2, and V1 by V2 will equal to P2 by P1. Therefore we can write this 2.303 nRT log P1 upon P2. Got it? This is all about isothermal reversible expansion. Now for irreversible process, what will be the isothermal irreversible expansion? It will be, work will be minus P external delta V. It is equal to minus P external V2 minus V1. That's it. And what about free expansion? If there is free expansion, then P external will be 0. For free expansion, pressure will be 0, and therefore W will be 0. And therefore here in this case, as temperature is constant, delta U will be constant, delta H will be constant, W will be 0, and delta H, delta U, W and Q all will be 0. And in this case, only delta U and delta H will be 0. This is all about today. In next class we will see what are adiabatic processes. Okay, thanks for watching, and if you have any doubts, then please ask me.